So this is the last case for deterministic, the actual stress and random yield stress. So this is case number 4. Case number 4. Then for the case, this is a normal. When probability model is a normal, as you know, is much simpler using the standard normal distribution model, and very easy to compute. You can get the result with not the closed form solution, but using the standard normal probability table. So, log normal distribution situation, there are lots of application also, and very nice to get the solution really fast, but easy to make mistakes. So I want to conform through the midterm exam. Of course, I'm going to give you the normal and the log normal situation to make sure you don't screw up, okay? So log normal is still very simple, but still can make a mistake easily. So this is, of course, this is deterministic. In this case, deterministic situation. So for probability model for the normal distribution, so you have to start always the probability density model, then you can integrate to generate the cumulative probability distribution model, and sigma y. Again, nothing to confuse. This is a deterministic value. It's like a required value or specific value for yield stress. And this is equal to 1. What's this? After a weekend, it's getting a little bit rusty, but what's this? Standard deviation of the yield stress. That's what we use this notation, because sigma, capital letter of sigma and small letter of sigma is kind of confusing, so we just designate this as a standard deviation of sigma y, okay, yield stress. This is exponential minus half sigma y mu sigma y and b, standard deviation sigma y and the square. If I make mistake, just let me know. Minus infinity to infinity, the full range. So now we wrote this down quite a few times. You'd know this. So now Fy, so yield stress is random, and you have to integrate this guy. So for integration, so I'm going to say this is integrate minus infinity to sigma y fy. I can just use this. I'm gonna just leave it like this. Then now you can introduce the standard model normal distribution expression. Conversion is we have done a few times, and sigma y over b if it's there's any mistake, point out. And what's the expression here for phi? Expression for phi, let's say this is x, is equal to, so easy to remember is the mean is 0, standard deviation is 1, shifting to the origin of the coordinate. So this is square root of 2 pi minus infinity to x exp minus half. This doesn't make any difference because it's integration parameters. All this is in the table, or you know, you can look at the what do you call it? Any program nowadays, it just has a value. Okay, now this value is a constant, given, deterministic, and yield stress probability model of the yield stress happen to be normal in this case. So now it's all set to cast into the probability of the failure or the reliability expressions. So it really doesn't matter. So reliability expression is probability such that sigma s and sigma y, s and y, actual stress and the yield stress for reliability has to be which way this would go. This way or this way. Top or bottom? Set top. Why? It's reliability, yield stress. Easy way to remember is the yield stress has to be larger than the actual stress. That's what you're looking for, the probability. So here is, you can have a 1 minus probability. You can say, well, first this is sigma s, sigma y, or 1 minus probability of failure. Usual expression in structure mechanics problem happen to be the probability of the failure, and the processing reliability they use R, which is 1 minus PF. So 1 minus PF by looking at from here, looking at that, which is equal to, this is now cast into the cumulative distribution function. So here I should put this guy like that. One is reliability, the other one is a complement. and Fy and the sigma what? Because it's there. The next step is 1 minus. So phi expression, I'm going to put the sigma y saying that the yield stress is random. So once you got that, so sigma s minus this is mean value, sigma y, and this is b, variance square, you can use that one. So if you look at you have a different expression in my note, and you divide it by up and down by mean value of yield stress, then you end up dividing this by mu, then which is called the central safety factor, which is phi y, which is n1 minus 1. This is, what's this? This shouldn't be sigma y. Correction in my note, right? Because you have to divide by up and down by mu sigma y. So it's a 1. This is n1. This guy you divide by mu sigma y. So in my note 8-33, which happened to be this, which happened to be this has to be y. As the formulation is done, you can compute the reliability. Target is to compute the probability of the survivor, or reliability, or complement is the probability of the failure. That's I try to give you the since last Thursday, Friday I wasn't here, so last Wednesday I made up some application type simple problem using what you learned. So I want you to review from the beginning. Some of you, I see it, took the probability course or statistics course, and of course makes it easier. But I cover from beginning to this week's lecture. So for problems that is concerned, some are simpler, some are like this, you know. What happened for both mothers are a log normal distribution, for example. You know. So what's the probability of the failure for given situations? Depend on how fast the Higgs can solve it. Then I have to determine whether it takes 1 hour or less than 1 hour. I want to make up the problem which will take just about 1 hour. So that's what my plan is. Okay, So this is, so now this week couple lectures both are the random. You are exposed already for the case that both are the random situation. But so couple cases, and also what happened if two random variables like actual stress and yield stresses are correlated. So something like the 3 different cases I'm going to review. So I want you to follow 100% on this one. And actual loading and the resistance or strengths of the materials are usually not well correlated, statistically really quite independent. So that's a very good nature. But some situations, like I might mention fluid structure interaction problems, it has a certain degree of correlation between the loading and resistance. But okay, it's correlated, but it's very, very difficult to quantify or develop or find like a mathematical relation. You could say, oh, it has could have some degree of correlation for FSI situations, but how to present in numerical model, very difficult. So we know it has weakest link each other. So I can say mostly assumed independent. I'm talking about between the loading and the strengths. But among the parameters within the material property, like Young's modulus or deformations, the dimension matters. You can develop into some correlation model, much nicer than load and the strength. So, so third case is if there is some correlation, how are you going to handle that? So that's what I'm going to present it. That covers about Isaac's book, about chapter 2 through chapter 5, and the rest of the chapter, couple of chapters, they are some special model really developed by a particular person, so it's not really quite general. But the case I covered is quite general. It's 2 different parameters I use, stress and yield stress, things like that. Then that present really well. Then after that, by the Wednesday or Friday, I'm going to start the general case, and then you can really solve some real world problem which you might face yourself. Then we're going to start something like a Friday, first order reliability method, pretty detailed, not just skimming over. Skimming over, problem is you can't solve it. You can capture the concept. Concept is already I explained enough, like R and S, deterministic sigma S and random sigma Y is done. But once you getting into the general situation, it's quite difficult, but first order is pretty elegant, and I'm going to send you today or tomorrow about 60 pages maybe. Professor Du's chapter 7, still he's writing. He's a professor at University of Missouri. Among the books I read, that's kind of the best description. Maybe because the way he writes English is maybe he's Oriental, Chinese. Maybe that's the reason. It's very well written. I didn't know him personally. I called him up when I really read it through. It was very well written, so I praised him. Hey, Professor Du, you did it very well. So Jungan mentioned he took another course, couldn't understand what's going on. But he has to apply to compute the reliability of his system. Then he has to write the code. In 2 weeks, I guarantee you can write the code, your own code, first order reliability model. Then I want you to start working on the project somewhat nicely, not just to complete the course project, some meaningful project. I want to, 3 of you, as a team could generate really well. Okay, you have all the tool you have, all the tool, MATLAB, MATCAD. Some are using, Arlene is using MATCAD. The rest are using MATLAB. Fantastic tool, but what I'm afraid is even MATLAB, they have all the sub-program, sub-tool. So well, you don't have to do any programming for that inside the module that you just pick. Well, that's the way it's supposed to be. Then if you don't be careful, you lose how to really set up your sub-program, because you just get it from within the MATLAB. Oh, this is one you can simplify it. But if you don't be careful, then later if I say, oh, your answer is wrong, your reliability is wrong, then you could say, oh, MATLAB did it. I didn't do it, MATLAB did it. That's not the right expression. You use the MATLAB program in the wrong way. You have to be kind of careful. Okay, now maybe a couple of hour lecture. Sigma S, sigma Y, both random. This is random signal. Both are the random. The case I'm going to do here is, of course, I want to do easy one in the class to really show the concept. And normal. Another case is log normal. I could generate, you could generate, that's what I'm leaving the rest to you. you can generate the case. This is what we're going to do, normal. You could do, and this is the case. This is another category, could it be? Another category, extremal distribution is good to cast into the extremal, like Weibull distribution. So, or exponential distribution, you could say this is exponential, this could be normal. All different combination you could do it, but it really doesn't matter because approach is very close. But these two are somewhat special because you can eventually cast into the standard normal probability model. For these other cases, you have to numerically integrate. For the two parameter case, very easy to integrate. But if it's a 3, 4, 5, it's not easy. Then another approach like the first order approach or second order approach come into picture, then you can really solve the problem. And in the previous sections, I already cast this guy a little bit, and I'm going to quickly, a few lines, I'm going to quickly review, I can say. Probability of the failure. I would use more for probability of the failure, but who cares? Reliability is simply complement of this guy. So still two parameter, probability and sigma y minus sigma s is less than equal to 0, which is in equation sense y minus sigma s less than equal to 0. This is really showing the region of integrations. Easy way to say, okay? Region of integration, region. And for the region, you remember the chapter 5, someplace, I show you the sample case for the FM. FM is this, I call the M. What do you call the M? That's a safety margin. That's what the y minus s. In this case, here, I'm going to say this is weird. Is it too much on this stuff? Too much, isn't it? I don't have to write this. How about simply say RS, DR, how about DRDS? How about changing this guy? RS. What do you call this? We have done that. And random variables are 2. That's simply joint probability density function. Up to the two, like a joint probability density function, you can really draw in the 3D view, then you can really see the everything in the graph. But if it's going to 3, then it's getting difficult. So that's what you have to integrate. This is, of course, the double integration, because it's really integrating in the given region. I didn't bring, I don't know, maybe I have here. In this region, you have integration of one region, integration of another region, right? You remember? Then what do you see there? I should have it here, but in section 5, you should have it. It's a volume, you can see that. And the volume of the probability, for the probability of the failure, is toward the edge of the graph, which is very low. Usually, always low, like a 10 to the minus 4th power, 5th power, 6th power. Then they generate, as I mentioned, the problem. And that's what the joint probability density function. If sigma y and sigma s are independent, then if it's independent statistically, of course, and very simplifies. When you marry, as I mentioned, everything, man and woman, they have to agree each other. Otherwise, we can't take the action. But when Kiwon wants to go to Busan, you don't have to ask Jin-gyun for approval. You don't do that, right? Because you are independent each other. Enjoy the independency. Once you marry, everything is all joint. So you have to develop the joint probability density function. In this case, if it's independent, then what happens? You have your own, right? This is sigma y. And Jin-gyun is a totally different mode of operation, right? So F sigma y sigma s, well, I have to write this way, but anyway. So here, if it's independent, you can simply write as sigma y. This is because I treat this guy as a random. Then inside I want to put the random specific value. So I'm going to say ys. How's that sound? Then this is y multiplied by f s. Simplifies very nicely. For the joint, the normal probability density function, if it's a joint, it's a mile long. But for this one, for each, it's only half a mile long. And independent each other. When you integrate this to get you got up late, huh? Joint, then this guy is only the multiplication of integration of two different things, then get the result out. So that's what it happened. And of course, for the F sigma y, sigma s, ys is simply Fy y multiplied by F s. Very much it simplifies. Lots of applications for the case of independent. But another reason is degree of correlation, very difficult to represent by numerical model. But I'm not denying, I'm not saying it's impossible. No, it's possible, but you have to spend a lot of hours to develop into the numerical model. All the methodology, the problem developed for the last 20 years is solving this integration, believe it or not. Not just a two parameter, multiple parameter, multidimensional, 1 through n. Then eventually people saying, well, we developed the optimization technique as a part of the math program, mathematical program, that operation research people's core problem to solve. Then you heard the math programming, linear programming and nonlinear programming, depend on how they correlate. So then in the structure optimization area, the methodology has been developed heavily since about 80, the 1980 and on. They really pick out the math programming technique to apply into the structure optimization for aircraft design, for ocean systems design, and so on. Optimization for aircraft means minimum weight design, simply speaking. Or for other application, it's like cost minimization and profit maximization, vice versa. That's what is all coming. You can use all such a technique as a part of the structure reliability computation. So it's a tool. So nowadays, so people keep saying that it's a fusion. Everything is a fusion rather than developing based on the original idea of fusion. Just to put it together, put in a melting box, let it melt it all together, then you can use it. It's getting more and more every day. The one building they're building by the fund donated by one couple, of course it's all the couple, is a IT Yunghap Center, IT Fusion Center. So that's what they are doing. So this is, don't feel this way. First order reliability method is the only one to solve the reliability problem. No, there are tons out there. But this first order is about the beginning, and it can solve a lot of different class of the problem. You don't have to bring the optimization techniques into it, but you can solve that as is. So here, that's the continuations of that probability of the failure is, again, as I wrote down there, this is a probability such that R minus S is less than equal to 0, or you can write this one, and here I can put the independent assumption. Otherwise you have to back to everything over there. If it's in this case, you can do a little bit simpler. Same thing, I just happen to show a slightly different approach. This is very easy, nice to use a notation for the region. R is always less than or equal to S. And you can bring this guy, the double integration, of course, here. Then I can combine this into this first integration. Then after that, the second integration. And if you do the integration, then that I can cast that into FR, this guy. Notation is the matter, is Fy. Up to what? Sigma S. Okay. Oh. I have to use R. Oh. Y D Y It has to be the same parameter. So this is here, then it brings down there, and ds comes out there. This is up to the s. That's correct. So it's a single integrations using that. So I can say that for independent situation, PF, you can do the integration of f, this y, and s, or to make it integration parameters, sigma s t dt. For the two parameter situation, you can easily express as using single integration. Otherwise, back to all joint here. Okay, then For the normal situation, we assume, of course, uncorrelated or independent each other, and normal situation. Both are normal. And again, first thing you have to write is F sigma y. You know, next one is you have to write the sigma s. Then after that, you have to get the cumulative probability distribution function. So you can do this, but now you know this. So if I just write here b sigma y and 2 pi and the exponential minus half, right, sigma y minus mu y b, right. So you can write very similar way on this, right? The very similar way. Measure minus half sigma s minus mu b squared. And of course, you can write this guy as a range for sigma y. Mathematically, I can write this like this. Then you can cast for the limitation for the actual situations. You have my note for this already. So now the let, right? Safety margin calculation. So sigma y, you have to say let, right? Margin, safety margin. What's the mean? What's the mean of the safety margin in terms of the random variable? Expected value of the safety margin, which is equal to e to the minus e to the. What about the variance? Or in terms of standard deviation or the variance. So variance, you can say Vm, and I'm going to say this is Vm variance, okay, which is equal to the variance of we use a standard deviation form. So this is a standard deviation form of margin. Then this is a standard deviation This is confusing me. Look at my notation here. Standard deviation. Okay. And what's the equation? You have to this guy square plus this guy square plus b square. Seems like that, right? Right? Q1, yes or no? Who cares? Yes, right. Take a look at it. Way at the beginning. Standard variance square is equal to summation of component square. And now then reliability, you can cast the expression as a probability such that M was an inequality sign. Higher 0, M is equal to R minus S. This is equal to 중간? M is less than 0. Less than equal to 0 or less than 0? I think it's equal to 0 is R minus S. R is less than. Is it correct? This is a probability of the failure. If this is less than equal to 0, then which means R is less than S, which is probability of the failure. And what does it say? Jungon was wrong this time. You direct me wrong. This is it correct? The easiest way to remember is resistance is less than the R. This is a failure. So this is reliability is happen to be this. And of course this is 1 minus P. You can work on this, and I'll finish this up the Wednesday morning. Then it's easy, right? From here is what? Convert into the standard, the normal, the probability function, phi, right? Cast into the phi. And that's the easy way to remember. So I'll start right here. And I want you to review before you come Wednesday, log normal case. A little trickier, but very straightforward. But if you start confusing, you're going into the slump. And I want you to review not my note. I could make some mistake there. And then we'll review it. Then we'll move into the first order methodology.